today, the topic today of me is the dimensions of the popcorn graphs, which is based on the works from in St. Andrews with the collaboration with Dr. Alan Banerjee, John Fraser, and Dr. Han Yu. Professor John Fraser. Yeah. Let's go to the definition of the popcorn graphs. So given any t, positive real numbers t, the popcorn function from 0, 1 closed intervals to R is defined by the things like this. So it means for every rational number, x, which equals to p divided q, where p, q are co-prime and p is smaller than q. And then we take the values 1 of q to the powers of t. Otherwise, just to say, if the x is the irrational numbers, we just take the value 0. Well, as for the graphs of the popcorn function, we just say gt equals to the graph set of the popcorn function, and we refer it as the popcorn graphs. Also, for the completeness of this talk, we will define the full popcorn set like this. So just to say, ft is the unit of the p divided q with the 1 of q to the powers of t. However, here I would like to make just a quick remark that the set in ft do not have the restrictions of the co-prime settings. And for t equals 1, the ftx is also known as the Riemann function, and domain function, the range of function, etc. Also is also known as some properties like the popcorn functions are continuous at irrationals, but not continuous at rationals. I would like to share you some of the figures about the popcorn functions. The first pair is the original, or just the domain function, and the full popcorn set I mentioned before. And the left one is the original, or just the domain function, and the right part is the full popcorn set. Just to say, here I would like to give you a quick words about the construction of the popcorn graphs. So, as for the popcorn graphs, popcorn function says at t x equals 2, 1 of q to the powers of t, where as for the popcorn function shows, for any rational numbers with the form of p divided q, the shape will be like this. However, as for the full popcorn set, it means ft equals to p divided q, 1 of q to the powers of t. And just to say, p just smaller than q, which means we can have a check about these 2 points. So if t, if given t, so we can check a half, just to a half of t. Here's a point here. Another point is a half and a quarter to the powers of t. So as for the popcorn graph, it only have this point, a half and a half of to the powers of t. But as for the full popcorn set, it contains the points like a half and with the value of 1 of quarter to the powers of t. Since we can see a half can be written as the 2 divided 4 and 41 quarter to the powers of t. So that's the main difference of the popcorn graph and the full popcorn set. Well, this is the first option. And as for the next part, so as for the value or the form and shapes of the popcorn graph, the shapes will rely on the choice of t. For example, if we choose the t equals 1, there will be straight lines. But if we choose some t, just here it would be the t with 0.3 is the right one instead of the t equals 1 is the left one. And as for t, choose some numbers not equal to 1, for example, like the 0.3, the shape will be some curves. Yeah. Moreover, if we choose some values larger than 1 or larger than 2, we just have the forms like this one. This shape just like the concave or convex settings. So in this talk, we will talk about some dimensions. So I will give some minutes to have a quick review back on the dimensions we will mention in this talk. The first one is the box dimension. Let X be a non-empty bounded set. And then for any delta, we just define the n delta X to be the smaller ball covers or cubes covers of X with side length delta. And the upper box dimension, the lower box dimensions can be treated as the limit superior or the limit inferior of the logarithm, the values determined by the logarithms. And if the upper box dimension equals to the lower box dimension, we just say the box dimension of X exists and write to the box dimension without any lines here. And as for the R-squared dimension, another important dimension in this talk is the R-squared dimension. Well, I think some of us have known the definition of R-squared dimension in the ball settings. However, in this talk, we will adapt the case of the R-squared dimension determined by the cubes instead of the balls. We just say if X is the non-empty set, and for any X here, we just denote this cube XR with this thing, just to say if D equals 2, the X is the left bottom corner of the cube. So the R-squared dimension, one of the equivalent definition of the R-squared dimension can be defined like this. So just to say, if we consider all the cubes, just from cubes to the from the balls to cubes, we just have the definition like this. That is to say, in this talk, we will concern more about the covering numbers of cubes instead of the balls. And as for the R-squared spectrum, it means here's some restrictions to the smaller r. Yeah. And just a complement for the R-squared type dimensions, I just state the quasi-R-squared dimensions and the quasi-R-squared spectrum, also known as the Canadian spectrum, I think. Yeah. So as for the quasi-R-squared spectrum, the restrictions shows that the small r have upper bound related to the capital R to the powers of 1 of theta, but but the R have a sense of freedom from 0 to the upper bound here. Notice that the quasi-R-squared spectrum is monotonic, so we just have the definition of quasi-R-squared dimension like this. Here are some properties we will use in this talk. So for general theta, the R-squared spectrum and the quasi-R-squared spectrum have the property like this. And here I would like to give a quick comment that for some fractal sets, the quasi-R-squared dimension will be strictly smaller than the R-squared dimension. Here's one of this. Another one is the limit behavior. Just to say, the limit of R-squared spectrum, if the theta takes value to the 0, it approaches to the upper box dimension. And if theta tends to 1, and it approaches to the quasi-R-squared dimension. Moreover, if there is some value theta 0 such that the R-squared spectrum approaches to the quasi-R-squared dimension, we just say for the rest of the spectrum, we always have the R-squared spectrum equals to the quasi-R-squared dimension. Another thing we will talk is the intermediate dimensions. So the house of dimensions can be defined by house of content. And just for this case, we just have the definition of intermediate dimensions like this. Moreover, the bounds from R-maps will be useful for the talk today. Yeah, just like this. And then in R-maps paper, the lower bounds of intermediate dimension will be helpful for the talk, since if we have the R-squared dimension of F and the box dimension of F, it will give some information about the intermediate dimensions. Well, let's come to the result of my recent progress with collaboration. So for any T, it's not to see that as for the house of dimension, the packing dimensions of the popcorn grass and full popcorn set, they will all equal to 1 because of the countable stability. But as for the box dimensions, R-squared spectrums and R-squared dimensions, it's say if T ranges from 0 to 2, we just have the exact formula of the box dimension related to T. Moreover, As for the alpha spectrum, we also have the exact formula like this. Just to say, since we see the graph for the beginning of the talk, it says if the t changes, the shape of the popcorn graph also changes. So also the box dimension and the alpha spectrum also determined by the choice of t. As for the intermediate dimensions, these similar things also happen. Just to say, if a t ranges from 0 to 2, the intermediate dimensions also determined by the t and the choice of theta. Yeah. So this example also shows that the bounds for our paper is sharp. And by the natural arguments, we can see that for the t larger than 2, the dimensions all equals to 1. Yeah. So that is the recent result on the dimensions of the popcorn graphs. So for the following, for the rest of the talk, I will just show you some intuitions to how to understand the popcorn graphs and their properties. And if time permits, I would like to share you some recent research interests of me. Now let's come to the intuition of the popcorn graph. It's just to say, given any t. So how to understand the popcorn graph at first? It's just to say, I think I need to draw a picture. It's just to say, a natural argument or just the intuition to the popcorn graph. Just for sharing the ideas, I just consider the case of the t equals 1. Yeah. I just say if the popcorn graph is drawn like this. I hope that the figure will be cracked enough for the talk. I'm afraid. So it just to say, if the popcorn graph, if the shape of popcorn graph look like this, so how to consider the covering statement or how to consider the covering arguments for this? So a natural idea have aroused from just having a line cutting here. For example, if we choose some certain horizontal lines L to cut the popcorn graph into 2 parts, and for the top part, you can say 1. With the covering number of 1 just determined by the points in the region 1. Just to say, if we consider the coverings in the region 1, I can just compute the points inside. However, as for the region 2, we just consider the natural delta mesh. Just we consider the cubes with side length delta to have a tuning process of this. So as for the natural intuition, we just say if we consider the covering segment of the popcorn graphs, we just compute the point in the region 1 just to say just the part of the top part, and then we just consider the delta mesh on the bottom like this. Okay. So for the rest of the talk, for simplicity, I just use the floor function and field function for some notations. However, I just talk more about the intuition and the ideas more than the details. So here just the complements. Okay, so for the general ideas of the box dimensions, just follow from the natural intuition like this. So for the upper bound, we just directly prove the upper bound looks like this directly from the natural intuition here. However, as for the lower bound, we will apply the Chern-Dodge inequality at first and apply the differentiable type estimates. Yeah. So as for the upper bound, we just following the ideas of the natural intuition. Just to say, if we cut the popcorn graph into 2 parts, one is the top part and compute the points inside, and consider the delta mesh cover on the bottom part. We just have the approximation of the covering, so we just have the upper bounds directly. But as for the lower bound, we will introduce a horizontal views here. So just to say, we can consider the popcorn graph like just by the horizontal part just to show for example, yeah. Yeah, I just like to say for popcorn graph, and we just say here's a half and a half. And as for here, a third and a third, and a third, to a 3, and a third. Also, if we consider a quarter serve, and you can say a quarter and a quarter, a 3 or 4 to the a quarter, etc. I just should say what is a horizontal means. I just should say if we consider the popcorn graph at the horizontal length like this. So if we choose some denominator of the n, and the wheels can be treated like this, and the idea for getting a better lower bound just to show if we cut the strips, if we cut the popcorn graph into the strips, and if we have the lower bound for each strip, we will definitely have the lower bound of the popcorn graphs, the dimensions for the lower bound popcorn graph. However, as for the coverings of the each strips, it just to say we will apply some techniques from the Differential estimates in self-bounding approximation. So let phi be a positive real number, real functions, and we define E and phi to be just a points for every x given fixed n, and we just consider this x just have a distance of n of k at loss of n of the psi n here. And as for the differential estimate, it shows for different m and n, and the Lebesgue measure can be controlled by the psi m and psi n. Yeah, as for the estimate of the popcorn graph, we just choose some special functions on the differential type estimates. Just to say, if we choose the en psi, the psi here, we choose the psi n equals n times delta, and we just have the horizontal differential estimate for popcorn graph. Since we see just now the Lebesgue measure can be controlled by the psi m and psi n here, but just now we just control it like the 4m plus times delta square. So it just means how to consider this coverings of this strip. It's just to show if we project it onto the x-axis and consider the two delta length intervals of the points here. So we just have this. And for the lower bound estimates, for the cubes, so a natural covering estimate in horizontal settings, it says the covering number can be controlled by the Lebesgue measure in the strips, in every levels of the strips. And as for the Lebesgue measure estimates, we just have the Dodge inequality. As a result, so if we separate the popcorn graph into strips and by the covering estimates of the horizontal strips, it just to say for every strip, the lower bound can be controlled by the Lebesgue measure at first. And as for the Lebesgue measure, we can use the Dodge inequality to get a final lower bound here. And as for the lower bound estimates, the denominator part is, I think, not so hard, but the denominator part will be controlled by the differential estimates. Yeah, so that is just using the covering estimate in horizontal strip at first, and Dodge inequality later, and Euler's torsion function just to control the lower bound of the denominator. And we use the horizontal differential estimate for the denominator. We just have the lower bound like this, and I'm taking the sum from some values determined by by the just the values determined from the upper bound. So we just have the explicit formula. Well, that is the box dimension stuff here. So as for the Oswald spectrum, the idea seems a bit similar to that of the box dimensions, but some slight changes also happens in the Oswald dimensions and structure stuff. It just say if we consider the upper bounds of the Oswald spectrum, we just use the idea directly from the box dimension. However, as for the lower bounds, sorry, here should be GT. And as for the lower bound, we need to apply the Dodge inequality again at first. However, we need to prepare another differential type estimate just for the local settings. Well, as for t larger than 2, just by the natural argument, we can say directly that for Oswald spectrum, equals 1. Yeah. So, right. Here is the upper bound estimate, just similar to the idea from the box dimension. And just to say, if we cut the, I'm sorry. Now, as for the local settings, so if there is a cube from the local part of the popcorn graphs, I just separate by the line L at first and consider it into two parts. And if we consider the upper bound of the alpha spectrum, we just compute the points upstairs at first, and consider the delta mesh cover at the bottom. So naturally get the upper bounds of the alpha spectrum. As for the lower bound, we need to have another intuition or just a vision about the popcorn graph called the horizontal vision. It means that if we consider the left part of the popcorn graph, it can be expressed like this. So it can be expressed like the L divides Ln plus I, and taking the values of one of Ln plus I to the powers of t. Here I would like to give an example just to say we can try to see, for example, like free right. Since we see if we take the values of 3 and having the I from 1 and 2 and taking all integers n, so we can see these two values are always co-prime to each other. Yeah. And under these cleft wheels, we just just if for the local part of the popcorn graph, just look like this. If we separate the popcorn graph like the cleft wheel like this, so just to say, here we cut the popcorn graph inside of the horizontal lines, but the the collapse lines here. Sometimes it will be collapse curve if the determined by change by the values of t. So if we have cut the popcorn graphs into the just into the shapes of just into the cleft wheels, and we choose delta and theta just to n times plus one of this, and with the to the power of 1 of theta, just to say if we cut the popcorn graph from the left part with the height delta and theta, and just the by the cleft lines here. And then we just consider that what its FL means. It's just to say for each line here, we just project it into the x-axis and covering by the 2 delta length again, interval again, yeah. So under these settings, under these cleft settings, we just have another talk about just analogs result on the covering estimates in cleft strips, just to show as for each cleft strips, the covering number also. And just to say, if we consider the covering numbers of the cleft strips, the lower bound can be also determined by the Dirac measures on the points inside the cleft strips and lines, and also motivated from the points and structures inside the sets popcorn graph. We also have the local different shape estimate, just motivated from the original different shape estimates and the structure of the popcorn graph. So yeah, under these two settings, we just have a quick proof on the lower bound of the alpha spectrum of the popcorn graph. It's just to say, but at first we just cut the curves into the cleft strip at first, and using the covering estimate in cleft strips to add those inequality and the different shape estimate again, we just have the decide the lower bound and taking the sum from the decide values, we get the decide arguments. So here is the proof of the alpha spectrum. As for the intermediate dimensions, we just have a definition-based proof. But if you have noticed that the alpha dimension and the box dimension, you can just use the alpha dimension and the box dimension to get a decide bound for the intermediate dimension. And for the upper bound, we just use the natural arguments again. And as for the lower bound, we just use the alpha dimension, the box dimension to get the desired ones. For the rest of the time, I would like to share some research, some recent interests of me related to the popcorn graph. So as for the definition of popcorn graph, says sorry for erasing this. We just say if x equals, if given a natural and rational number, x equals to p divided q. For each level related to Q, the points of the level Q will be determined by the number structure of the Q. For example, if we say oh sorry, I just say if Q equals to 4, the possible choice of P divides Q co-prime settings will be determined by only just to say the possible P can be choose only 1 and 3. Yeah, since we see if Q equals to 4 is not a prime. However, if we choose Q equals to 7, the possible P can be chosen as the 1 to the 6. It just should say if if the Q is not a prime, some point will be lost in the graph. That if the Q is the prime number, the points in this level will be fully just adapted. So just to say, if given any sequence of S, just a subset of natural numbers, I just have the S popcorn graph together and the S popcorn set. So and my current research interest includes is if given a subset of the natural number S, so can we say something about the general bounds of the S popcorn graphs related to the structures like S, for example, like the densities or logarithm densities. Another one is that since as for the prime numbers, the levels will be collected well. So if there is some just some well-known sequence, for example, like the prime number sequence, can we say something about the explicit values of the dimensions and structure of the prime popcorn graphs or other settings? So I think yeah, I think I'm happy to share my ideas again, and thank you for attention. Yeah, thank you for attention.